got her out of Germany, because the Germans would have killed her. She was Jewish. She escaped. A man named Niels Bohr, a very famous man, got her a position in Sweden. While she was in Sweden, she gets a letter from these two chemists, Hahn and Strassmann, back in Berlin, that the materials left over from the reaction had barium in them. They didn't have barium when they started. And she and her nephew, Otto Frisch, realized that the atoms of uranium that had picked up neutrons had split and had given off gigantic amounts of energy per atom. Now, she didn't know that that would happen fast enough to make a bomb. But she told people, she told Bohr. Bohr was coming to this country to a meeting at Princeton. He told a lot of other physicists. And the news, the great secret, was out. So basically there was no secret of atomic weapons. Now, you still didn't know that you had enough neutrons coming out to make a useful bomb. And the bomb, one neutron goes into a uranium-235, splits it, and you get all sorts of things. One particular atom will split and give cobalt, another will give strontium, another will give some barium, another will give some iron. A whole range of products are made. It is a statistical process. But you still don't have any useful energy or bomb unless you get more neutrons back. And so again, Leo Szilard was the guy who borrowed money to rent some radium as a source of alpha particles, to irradiate some beryllium to get neutrons, to treat some uranium with, and he found that you got the neutrons you needed to make a bomb. Now the question still is it the right rate? If, let's say, uranium picks up a neutron, one neutron comes in, and it waits 2 weeks to split. You can't make a bomb out of that. And if it splits exceedingly quickly, you can't make a bomb either, because you can't get the thing assembled. As far as the neutrons are concerned, the thing blows itself apart. You have to have just the right rate, and it so happens that there is just the right set of rates of reaction to make a bomb. Szilard and a couple of other physicists persuaded Albert Einstein to send a letter to President Roosevelt that you can find in the history books, suggesting that the United States start a project toward a bomb. The aim of the bomb was to beat the Nazis to the bomb. That's what it was for. They knew that the Nazis had restricted shipments of uranium from Germany. They knew the Nazis were trying to grab all the uranium in Germany. And they knew the Nazis had shut up about any uranium work. So they thought the Nazis were after the bomb. Turned out the Nazis made some mistakes in their science, so they didn't get close to a bomb. We made mistakes, but not that fast. We got a bomb. So that's what the bomb was about. In natural uranium that you go mine, right here in Tennessee, there's uranium in the phosphate rocks. Small amounts of uranium. All that uranium would be mostly uranium-238. It won't make a bomb. It'll make a hydrogen bomb work better, because uranium-238 will undergo neutron-started fission, but not easily. You have to have enormous temperatures for that to happen. But if you want to be able to make a bomb yourself at atmospheric pressure and room temperature, you make a bomb from uranium-238, which is only one atom out of every 140. So you've got to isolate this one atom to be able to get a satisfactory rate for a bomb. Now let's go back to old chemistry. Until 1945, when the Hiroshima bomb dropped, all explosions in this world had been chemical reactions. Gunpowder, 3 chemicals go to a bunch of chemicals. When TNT blows up, 1 chemical goes to a bunch of chemicals. The atoms don't change, the chemicals change to get these rapid releases of energy that are used to propel a projectile or to break a submarine in two. RDX that Eastman made during the war was made because it would crack the back of a submarine. Ordinary explosives wouldn't do that. That's why they wanted RDX. That's why the Army was working with Eastman. Eastman was running the Holston Defense place to get that particular fast chemical explosive. But in an atomic explosion, it's the atoms themselves that change. And there are very few atoms that will do that. Hydrogen will change if you get it hot enough. We'll talk about that a little later maybe. And uranium and thorium up at the other end of the table, the periodic table, big heavy elements, they'll do it. And then the synthetic element, plutonium, will do it. I knew nothing about plutonium during the war. That was after the second bomb occurred. So, Roosevelt authorized this project to start. It went very slowly for a long time until the fall of France. And when France fell in the war, Roosevelt authorized an enormous increase in the size of the Manhattan Project. It was called the Manhattan Project simply because there were offices in Manhattan of the Corps of Engineers, and the first man in charge of the project was in Manhattan. It made a good code name. It was the largest industrial project in the history of mankind. There were about 500,000 people involved in the Manhattan Project, which wound up with 2 bombs. In Oak Ridge, the big buildings of Y-12 contained machines called Calutrons, California University-trons, designed by Lawrence, Professor Lawrence. That I used to have lunch with him, an interesting man. But again, we knew nothing about bombs. My group worked along just fine. We learned how to make uranium tetrafluoride. I happened to, being the chemist in the group, run by an engineer and a senior chemist, I happened to ship the first product to Los Alamos that was hot material. I had the world's collection of uranium-235 in my fire safe at one time. Fortunately, then they had the production department ready. We'd finished the research work, and I could go on and learn other pieces of the uranium chemistry, help clean up some of the messes we had, learn how to clean them up. And the production department took over the manufacture of uranium tetrafluoride from the enriched uranium-235 and shipped it. There was one huge problem occurred at Y-12 during the war. I want to talk about it for just a moment. Just about the time I got there, the first big buildings that had been finished wouldn't work. There was no pilot plant for Y-12. Now that decision had been made by the president of Harvard University. How did he get in the act? Roosevelt had a man under him called Vannevar Bush in charge of all the technical work in the war. Bush couldn't handle all the radar, and synthetic rubber, everything, all the other developments we had to have by himself. So he had deputies for various parts of the work. And a chemist named Conant, who happened to be the president of Harvard, was in charge of all the atomic work. Conant had decided there'd be no pilot plant. There wasn't time for a pilot plant if we were going to get this bomb ready to use before the Germans got the bomb. So there was no pilot plant. So we built these big buildings, first big building, and it wouldn't work. What was happening when the Eastman people took the big magnets apart for the electromagnetic separation device that Lawrence had designed, called the, as I said before, called the Calutrons.